I'd just like to start by saying it's not all about me. We've got quite a lot of people working on this project that I'm going to describe today. So there's a few of us from St. Andrews. Adam is a PhD student. He did a lot of the work here. I didn't really do much on this. I'm just here to present it and take all the glory. But really, Adam was the guy who did all the work. Wojciech and Olek from Poland. Wojciech, you probably know. If you have any questions about what I'm going to present today, come and see me, Wojciech, or Olek, and we'll be delighted to try and answer anything that you might be concerned about. So what are we doing at St. Andrews? Well, we've been doing, obviously, research for a long time, 600 years. But recently, we've established quite a lot of collaboration with EU partners. One of this is a new EU project called RePhrase. This started about 10 months ago in April. It's quite a large project. It's €3.5 million budget, so it's not a small project. We have quite large partners, some huge mega corporations like IBM. We've got other big commercial partners like EvoPro. We've also got a lot of academic collaboration. We've got University of Pisa, Madrid. You can't quite see that, but that's Torino. And what I'm going to describe today is work that's come out of this EU project. So it's ongoing work, and we've still got over 2 years left of the project remaining. So anything that I'm showing you today is really kind of early days. It's not established research. So what are we trying to achieve? I'm guessing everybody who's here has gone to university and studied computer science. If you haven't, then don't worry. But I guess what your lecturer always tells you is that how to write parallel programs is always like this, right? So you always have perfect distribution, puppies to sources. Nothing can be described without cute puppies and sources, I think. So all the puppies get the food. However, what happens when we go out into the real world, we get a job, and we want to start writing this code? Well, this usually happens. You get absolute chaos. So here you get everyone fighting for the same resource. Puppies always very boisterous. And it's the same with parallelism. Nothing ever works out in practice. So everything that you're taught in the classroom, just forget it. Basically, none of it works. So what I'm going to tell you today is basically how to do it properly. So some of the real challenges that we have to face when we write parallel software. So the things you were taught in the classroom, the things on the left, they don't really exist, unfortunately. It's a theoretical assumption. So what we're trying to do is to solve real problems. I know this is a research track, but this is really applied, the research I'm showing you today. There's no theory, there's no horrible Greek letters. Don't get worried about that. We're doing real software engineering work, trying to solve real challenges. Some of these things include things like building new tools for testing, debugging of parallel applications, things like quality assurance, introducing new standards for parallel software, for writing parallel code, deployment on different types of hardware. This is becoming a very hot topic recently, things like CPUs and GPUs becoming very trendy. Also many-core FPGAs, things like how we schedule these applications on these big hardware platforms. How do we maintain software? It's very important. You write software, you need to maintain it, you need to deploy it, you need to keep your customers happy. This is how companies make money. So these questions are usually never answered in academic papers. And what we're trying to do is to really try and understand this problem, really think about it in a proper applied way. So what we're doing on RePhrase is taking quite a different approach. We're kind of looking at different areas of software development. So things like requirements capture, design, implementation, testing, deployment, all these kinds of agile or waterfall type software development practices, and try and apply them to parallel programming. Because really parallel programming is no different to any other type of programming. It really needs lots of thought, lots of design, lots of verification to test that it's correct. And probably actually more so than sequential programming. It's much easier to do something wrong when you're writing parallel programs. So what this talk is about today is one aspect of this research. So it's called program shaping. And what this basically means is that it's all about restructuring a program. Could already be a legacy application that you've got. So it could be an old application. It could be a new one. It doesn't really matter. And restructure it in a way that you can enable an introduction of parallelism. So you can enable just to put the parallelism into it very easily. Usually putting parallelism into code is actually quite easy once you understand it. The biggest problem with it is that most programs, they're not in the right shape that you can just put the parallelism in. So people do it in all these incredibly complicated ways, which is really not the right way to do it. And you usually don't get much parallelism out of that as a result. So what we're doing is taking a different approach. First, you restructure your code to make it a nice, hygienic, safe type of application, and then you introduce your parallelism into it. And for example, some of this might include things like removing side effects. So side effects, really you don't want side effects when you're having something running in parallel because things can interfere. Seems quite obvious, but a lot of people overlook that. Things like eliminating dependencies. A dependency is sequential. Okay? If you have something that depends on something, it's sequential. You can never parallelize something that has a dependency. Okay? You have to remove it. Might seem counterintuitive, but that's life, unfortunately. Most of these approaches are quite ad hoc. So people just do this by hand. You get an application and you just randomly try and change it until you get something that works. Okay? This is very non-trivial. It requires a lot of knowledge. You usually have to be an expert in the application that you're writing. If you're working for a big company, you might be given something with thousands of lines of code. You really need to know the code very well and very detailed to be able to do this type of work and ensure that it's correct. You also need to know a little bit about the language. How do the libraries work? How does the language work? How can you exploit it? You need to know about parallelism. You need to understand how parallelism works in a particular language you're using. So there's quite a lot of things you have to think about and juggle to do this task properly. So what we're going to show you today is a technique called refactoring, which I'm sure everybody has come across. We're going to use these refactoring techniques to kind of automate this process. So automate the process of restructuring applications, so then you can just introduce the parallelism, which is almost a kind of a trivial step afterwards. And hopefully that will make sense later. So what is refactoring? Well, refactoring's been around for a long time. It's the academic way of describing it is it's a conditional source-to-source transformation that preserves functional correctness, okay, which is almost meaningless, I guess, to most people. What it is, it's a tool that allows you to restructure code. So if you use Eclipse, you can do things like rename variables. You can move classes to different functions. You can add parameters to things. And the tool will do all of this automatically for you. So it will do all of the checking. It won't let you rename something to something that already exists, for example. It won't let you move something to a file that will introduce conflicts, etc. So it does a lot of all of this automation for you. And it also rewrites the code and lets you see the result automatically. So we're going to use it for parallelism. They help you with this process because they avoid introducing errors. So a tool can do all of the work for you. You don't need to think about how you're going to write parallel code. It knows how to do it, so just let it do it. You can give some input, and you can choose from a huge range of possibilities, and then just select the one you want. It's quite easy. The work today has actually been implemented in a refactoring tool called Wrangler, which is implemented for Erlang. This has been around for a few years now. It was originally developed at the University of Kent. It's an extensible tool, so you can build refactorings into it, and we've exploited that. And the work I'm going to show you today builds on top of that technology. But if you're not using Erlang, it doesn't matter. What I'm showing you today can be applied to any language. It's completely generic. So don't think what I'm showing you today only applies to Erlang. It doesn't. Okay? It's a high-level idea that I want to get across to you. So another piece of technology that I'm going to use is something called an algorithmic skeleton. So people probably have seen these, but they've never heard the term. So it's basically just a high-level abstraction. It's just a function, okay? Function that encapsulates some parallel behavior, and that's all it is. So just think about these things as just normal, composable, nestable functions. In principle, the idea of a skeleton is completely language independent. If you use C++, you have parallel skeleton libraries like TBB, OpenMP. Erlang, we've implemented our own library. I'm going to show you that in a short while. Haskell, you also have equivalent libraries. Doesn't matter. Whichever language you have, the ideas apply to it. And they work by, you only need kind of problem-specific code. So you only concentrate on the part of the code you want to parallelize, the kind of the building blocks of the code, and then you plug them into the skeletons. And then that's how you get a parallel program. Typically, they're implemented and collected in libraries. So you just call a function in a library, and you get a parallel program as a result. Okay? By the way, if anyone has a question, please just shout it out. Don't think you have to wait until the end if you don't understand anything. So these are just some examples of kind of the common types of patterns that we see most widely used in parallel programs. The one on the left here is called a parallel pipeline. So the way this works is you've got some inputs, some data here at the top. You've got some functions. So think about this like a function composition. It's kind of a nice way to think about it. So I've got some functions here. I take one of the inputs off, x0. I apply a function to it. I take the result of that. I pass it to the next function, which computes on the result of that, and so on and so on and so on. And where you get the parallelism from this is that each of these functions can execute in parallel. Okay? So while this second function is computing the result of this one can then get the next input and start computing, and so on and so on. So you get parallelism that way. On the right is kind of a more intuitive type of parallelism. It's a data parallel pattern. This is called a task farm. This works in a similar way. You have some inputs. You have some data you want to compute over. You have a function. And what it does is it takes these inputs, it sends them off to this function, which it distributes in parallel. They all churn away on their results, and they spit it back out, and you get some kind of thing that puts it all back together, and then you get the result here. So the parallelism here is you can basically take an operation and put it on different threads or different cores. So that's kind of a data parallel operation. Seems obvious, probably, but when people try and do this, they don't usually think about things like this. I see people writing Erlang code and they're thinking things of spawns, messages, receives. It's really low level. You don't want to be thinking like that. It's really not the way to do parallelism. These are nice, simple, high-level concepts, which I think really kind of get the idea across very well. Another example is a feedback. So this, basically what this allows you to do is to take any of the skeletons, for example, the ones that I've just shown you on the previous slide, you plug them in here, and you take the output of that. If it satisfies some condition, well, it's kind of counterintuitive. If it doesn't satisfy a condition, you stop, you terminate. If it does, you just plug the results back in. So it's basically just like a loop. So you can get the parallel operation, and then you can keep looping on it. And of course, these patterns are fully nestable. You can put farms in pipelines, pipelines in farms, etc. So we implemented a library for Erlang that basically is a parallel pattern library. It's called Skel. It's available at this website. You can download it. You can try it. It contains many different types of patterns, things like pipelines, farms, feedback, all sorts of different ones. It also contains hybrid skeletons, so it allows you, if you've got a GPU on your system, it'll allow you to use that GPU out of the box. So you can download the library and then start using GPUs. We've got various things on the website, tutorials, podcasts, all sorts of things. So if you're interested, please go to the website, download it, take a look. Thank you. And an example of how it works. This is an Erlang, a simple map operation in Erlang. We've got calling map function here. We've got some function called worker and some input. And if we want to parallelize this operation, all we need to do is change that map operation into this thing on the bottom. And what this is doing is it's calling our Skel library with a farm, which is the data parallel operation that I showed you, where the operation is going to be worker with the same inputs. NW then could be, I don't know, I might have 4 cores on my laptop, so I put 4. And I get 4 copies of my worker, and then I get the parallelism. Okay, so it's quite simple, kind of intuitive. So it's almost like a map, but you have to do a little bit more work, but not very much. So what I'm going to show you is how we're going to parallelize a multi-agent system. So a multi-agent system is built up basically in 3 steps. Firstly, we've got agents, which are intelligent, autonomous entities that solve some problem. So some function or worker that solves some problem. Then we've got multi-agent systems, which brings many of these agents together to form a system, so they work together. And then an evolutionary multi-agent system combines these multi-agent systems together with some kind of evolutionary algorithm. So some kind of way of evolving over some kind of condition. It's highly parallel because the agents are independent. However, it's not quite as simple as you might think. So what I've done is I've simplified the structure of the application and kind of broken it down into its main components here. What we've got here is a number of operations. First, we do some tagging. Then we build some migrants. It doesn't really matter what they do. It's not important. It's the structure that I want to get across. We do some grouping of the migrants. Then we send them to agents. And then we shuffle. And then we repeat, and so on and so on. So there's kind of a lot of different stages here that have dependencies here. We've also got loops. So we've got things that iterate. And then we've got something that kind of feeds results out. So looking at that, it's not quite clear exactly how to parallelize it, probably. Okay. I could show you the code, but most people don't like seeing code. I hate seeing code in talks. I just can't read it. It's just, I just see mess and I just can't see detail. But anyway, this is the code. It's quite complicated. It's several tens of files, hundreds of lines of code. This is kind of the main part of it. But what I want to show you is how we can use our program shaping refactorings to break this down and make it parallel. So what we could do is simply introduce a farm. So everywhere we've got a list comprehension in the code, like a map, we can just make it a farm, right? That seems an obvious way to make it parallel. The problem with this is it's incredibly inefficient. Creating the farm itself actually has a lot of overhead. So spawning processes in Erlang is actually very expensive. It's not. People think it's lightweight, but it's not lightweight at all. The problem is if your tasks are very small, the overhead of creating the farm just dominates it, and it actually slows your application down quite considerably. Also, the function loops, so it compounds all of these issues. So every time it iterates, it's again setting up farms, and the whole thing just blows up, and you get this huge overloading explosion of slowdowns in your code just doing that. It's much better to try and express the parallelism in a single operation, because that minimizes the overhead of creating all of the processes. So you want to minimize that as much as possible, okay? And just have one place in your code where you do the parallelism. It's much easier. But as the code stands, we can't do that. It's too complicated. We can't just make a single operation parallel. So what we need to do is we need to first divide up the code into components. So these are kind of atomic operations, things that are side effect free, simple functions that do simple computations. And then all we can simply need to do is just arrange them. And we're going to use several different refactorings that we've got that I'm going to describe in turn. So the first thing we need to do is to use this function called extract composition function, which takes all of this inlined code here and makes them into functions that we can just call. Okay. Seems quite obvious. Most people overlook it. So once we've got that nice structure in place, we can then start to group the operations together. So the first one is to group these three operations into one single operation. So we use another refactoring called compose maps. So it composes these together into one operation. After we've done that, we can simply introduce a farm here into this component here. And then once we've done that, we can then further parallelize it. So this is already a parallel version of our application. But now that we've broken it down into nice steps, into nice components, we can continue to parallelize it. So here what I've done is I've introduced a pipeline. So here's the first stage, the second stage, which was the farm, the third stage. And then additionally on that, I've created a feedback. So I've also made that a skeleton. So I've broken this down into three different types of patterns: a pipeline pattern, a farm pattern, and a feedback pattern. Okay? And the results, what I'm going to show you is just two different versions of this EMAS. We've got basically a concurrent version. So this is if you just read Joe Armstrong's book on Erlang. This is how you parallelize an Erlang application. The second one is a hybrid version that basically takes our Skel version, our refactored version, and tunes it much more. These are the optimization benchmarks. I'm not going to go into the detail. It's not really important. The results are very interesting. So what I've got here is the blue line. This is just the bog standard Erlang version, out of the box Erlang using spawns, sends, receives, etc. So you can see it kind of scales and then it just, well, just tails off. So you don't really get much more than 20 speedups on 64 cores, which is not really very good, to be honest with you. Using Skel, so using our refactorings in our Skel library, it scales much better, kind of over 40 speedup. And then using the hybrid version, so taking that Skel version and then tuning it just a little bit more, we're able to push it to almost, well, just under 60 speedup on a 64-core machine. So you shouldn't just take what a language provider gives you as a parallel implementation. It usually doesn't work. You need to think a bit more intelligently about it. Okay? This is just to show that in some cases, actually, the results are more or less comparable to textbook versions. However, it doesn't matter because what we're doing here is saving you enormous effort in your coding. So just using a concurrent version, the Erlang version, you write something like over 350 lines of code. Takes you 7 days. These were anecdotal results given to us by our partners on developing this software. The sequential program already took 85 days of effort. So this is effort on top of that 85 days. So if you're a company writing code for customers, this is very important. Okay? If you go over schedule because you're writing parallel code, you're really going to run into problems. So using our effort, okay, there's still 100 lines of code, but it takes a day of effort, and that's it. So I'm just going to wrap up. So what we've done is introduce some program shaping techniques. These allow you to kind of introduce parallelism very trivially into a code by just simply restructuring it. So then you can just think about the parallelism rather than all of the nasty details. We've gained very impressive speedups at almost zero effort, zero programmer effort. And of course, we can apply this to other languages as well. So future work is basically just lots of more use cases, lots more patterns, the usual stuff. Things like static analysis techniques, we can automate this process rather than it being a user-driven process. And that's basically it. I believe my time's up, so thank you very much.